This is Andy Schweitzer, and it's a little short video on how do I determine the pH of a salt. We're going to talk about pH of salt, but basically a salt can be either a weak acid or it can be a weak base. So I'm going to start off talking about basically how you determine the pH of a weak acid or a weak base, and the salt will be included in that. We have HF will be our first acid that I will talk about, hydrofluoric acid. You should be able to write out your hydrolysis equation and use H3O plus and F negative. In this case, the Ka will equal the concentration of the H3O plus ions and the F negative ions. And below here will be the HF. The water is not included because it doesn't have a concentration. It's a pure liquid. Now there are two factors that affect the strength of this, or I should say the pH, or the amount of H3O plus ions. That is, first of all, the initial concentration, right here, and then the extent to which it goes to product. This is called the strength, and is also the K. Alright, in this case, if I have a 0.1 molar solution, and let's just say it's 1 liter of volume, then I could say, okay, well, how much of this 0.1 will go to product? Well, if there's no reverse reaction, nothing fighting back, then all of it would go, and it would be considered basically a strong acid, and would have a pH of 1. But in this case, there is in fact a reverse reaction, and that is where this is a weak acid and this is the conjugate base, and it happens to be a weak base. Now this reaction, this reverse arrow, is this reaction. We have F negative, its hydrolysis equation, H2O yields HF plus OH negative. Now the F negative never comes by itself, and this is where the salt comes in. We have it will come in the form of a salt, NaF. This is simply a carrier at this point. Alright, now I'll talk about this in a moment, but with just the acid, this thing will in fact be acidic. The Ka for this thing, which you need to look up, is 6.6 e to the negative fourth equals, alright, stoic ratio, equilibrium, minus x, not playing a role, 0, 0, plus x, 0.1 minus x, and then x and x. Plug all these values in, x times x. I will use my shortcut rule here, 0.1, solving for this, multiply it times 0.1 is 6.6 e to the negative fifth, square root, and I get x equals the concentration of the H3O plus ions. I'll calculate that out. 6.6 e to the negative fourth times 0.1 equals, like I said, and then we'll square root that value, and I get x equals 0.00812 moles per liter. So that's of the 0.1, that's the amount that flipped over. You could easily figure out the percent ionization by this divided by 0.1 times 100 will tell you what percentage changed over. The negative log of that value will give you the pH at this point, and therefore the pH equals 2.09. Now, if I had just this guy, then again there is a reverse reaction, which is this one. But if I had a 0.1 molar solution of NaF, that would be equivalent to a 0.1 molar of just the F negative. And I'd run it through just like I did this one. Stoic ratio ending. Water will not play a role. None of this to really cause that reverse reaction to take place. None of this. Minus x plus x. There we go. 0.1 minus x, x, and x. Now, for this particular problem, we have this situation where what is the K for this reaction? Well, both reactions can't go 100% to product. They battle back and forth between each other. And the equation, therefore, is to figure out the KB is KW equals KA times KB. Given this, 1.0 e to the negative 14th equals my KA, which is 6.6 e to the negative 4th, times my KB, and I would simply divide this out and solve for my KB. KB ends up being 1.5, 1 e to the negative 11th. So whenever you're looking at a value, you want to know, okay, what does this number mean? Well, the teeter-totter point for this value here between the two is 1.0 e to the negative 7th. So when I have this in mind, and I know that when I see this value or this value, I know who has the greater advantage. In this case, the Ka is significantly larger than the Kb just by looking at it relative to its midpoint. Therefore, I know that the acid is much more strong than the base is. Meaning that if you have of the 0.1, it'll be able to push more over the product than will the base. So let's go ahead and calculate this out and see, okay, how efficient is this guy at actually being able to kick over the product. So the Kb equals the concentration of the HF, concentration of the OH negative, concentration of F negative. Plug your values in. We'll neglect this and plug in this value here equals 1.51 e to the negative 11th, and you solve for x. I will do that. And your answer is 1.23 e to the negative 6th. So that means of the 0.1, this thing could only push over at a given point in time this 1.23 e to the negative 6th moles per liter. Take the negative log of this value, will give you the POH, and then you can, in that point, you can get the pH by subtracting from 14. I'll go ahead and do that. And the pH ends up being a whopping 8.08. So it is slightly basic, but not a whole lot. The majority of my F negative ions stay as F negative, and only a few of them kick over. So if we had a solution where these were both present in a solution, I would include the 0.1 molar here and the 0.1 molar on both sides. So right, this would be 0.1. You would assume with equal concentrations of both, sorry, it'd be right here, equal concentrations of both base and acid, the acid or the conjugate salt, that would still be acidic, because equal concentrations, yes, but this thing is going to be much, much more acidic because of the K, the strength of the acid reaction. If you were to draw a picture out of what this thing actually looked like, say for example we have our HF picture. You would simply have a water solution and you have a bunch of HFs. Now a lot of times on AP exams they're going to have you draw pictures. If you can't draw a picture of it, then you really don't understand what it's like. And I would say that it's difficult to draw proportionality with this small, but I'm going to go H plus, F negative, H plus, F negative. Equal amounts of cations, anions. And if we were to draw this guy, we'd have a little different situation. We'd have F negative, F negative, F negative. 1, 2, 3, 4, 5, 6, 7. So let's go 7 of these. 5, 6, 7, and then one of these guys kicked over to an HF, and then OH negative, and then another. Let's just leave it at that. Okay, this one's got 2 of them ionized. This only has 1. I also would have every F I have here. I would have an Na floating around, and they are just simply spectators. Alright, any salt can be dealt like this. A salt is a ionic compound with a cation versus an anion. We talked about the hydrolysis equations for both the cation and the anion. All you have to do is plug in your initial concentration for the ice table and with its K value, and you can figure it out. Other common salts might be, let's say, NH4Cl. This guy, again, you need to remove the chloride. This is a spectator. NH4 plus H2O yields NH3 plus H3O plus. I'm donating here. This is my weak acid. This is my conjugate base. If I were to, the reverse reaction would be NH3 plus H2O yields NH4 plus OH negative. This is my acid. This is my base. This is my base. This is my conjugate salt. That's pretty much it. In a future video, we'll talk about neutralization and buffers.